First of all, I want to thank Professor Yanniouk that she offers me the opportunity to be here, present you my research. The topic of my speech are the long gamma ray bursts. It is in the scope of the Collapsar model. And my research is the jet propagation in that model, my research, and more specifically, from the point that the jet emerges out of the stellar envelope and continues its propagation to the interstellar medium. You can see here a first picture in order to get a first impression of what I'm going to say.
The pointer is right behind you.
Okay. As Professor Yanniouk said, I work with this work. My research is being done in association with Professor Vlachakis. Here is the outline of my talk. At the first part, I'm going to present you some classical observation and theoretical arguments that hold at the GRBs. I hope the people that they are familiar with the subject will not get too bored, because they probably have heard them many times. And then I will present you some fundamental constant quantities of the steady state relativistic MHD that I will use later when I will present you my results. The actual part of my research is the second part. And I will show you a model, a semi-analytical model that we developed in order to describe the planar symmetric rarefaction phenomena, and using a special set of solution that has the self-similarity property. Okay. Despite of being planar, that model, because it is a semi-analytical, and so it gives us a great insight to the underlying physics of the rarefaction phenomenon. And beyond this, it also predicts some scaling of the quantities that also apply to the axisymmetric jets, which I will describe next. And I will describe the axisymmetric rarefaction and an algorithm we built in order to integrate the superfast, to integrate the problem. If I have time at the end, the part C is my future research interest, and I will show you some ideas that I have. And in order to use more realistic condition for the interstellar, for the progenitor wind, and this is technical, some algorithmic extensions that we want to perform to our algorithm. Yes.
For the benefit of those who never learned Latin, but also Greek, you will explain what you mean by rarefaction.
Yes. Okay. As you probably know, the gamma ray bursts are among the most violent and energetic phenomena observed in our universe. The amount of energy are huge. If you assume isotropic emission, it's 10 to the 52 to 10 to the 54 ergs, comparable to the solar rest mass energy. And the radiation is very hard. It's gamma ray photons with energies about of 1 MeV, around to 1 MeV. The most impressive in this phenomenon is the duration. It's a duration. This release happens in the period of time from 10 to the minus 3 seconds to 10 to the 3 seconds, to 1,000 seconds. In that short period of time, the energy is released. So you can imagine that the hardness and the short duration makes GRBs a very difficult task for the observer to study and to study them. It is very difficult. You can imagine we first discovered them at 1973, and for the rest 20 years we didn't even know if these phenomena are galactic or extragalactic. It's so difficult. The first breakthrough came with the launch of the Compton Gamma Ray Observatory of NASA at the 1990, which recorded and from that very famous simple diagram that shows the distribution of the gamma rays among the sky. As you see, it's a homogeneous distribution, which means that it's not a galactic origin. They are not concentrated at the galactic place. So this was a first strong indication that it's an extragalactic phenomenon. And the confirmation, the definite confirmation, came later with the launch of the BEPO-SAX, another observatory that had the ability to locate the burst very fast and send an alert to the ground-based telescope, to the strong ground-based telescope. Those telescopes were able then to turn and look at the point of the burst and see what's there. And they find that there is a galaxy, what we call the host galaxy, the galaxy that hosts the explosions, the burst. So if they are extragalactic, that means that the energy that we received as observer in the Earth, that's huger. If it was a galactic, it should have been a small amount. And when you have, it's huge. There is no atypical light curve for the prompt emission of the gamma ray burst. Prompt emission is the main phase, the initial main phase that lasts seconds. But it's typical to have spikes whose width are 10 to the minus 3, 10 to the minus 4 seconds. So if you use the causality principle, okay, you can have a very rough estimation for the maximum extent of the source that emits that photons. So if you assume that source and that MEV photons and so much energy in that in radiation in that place, then you have what we call the compactness problem. What's this problem? Your own the photons are so dense, and your source they are trapped inside your source because they suffer this process called photophoton absorption that results electron-positron pairs. And so your source becomes intransparent to its own photons. And so the question is how you receive them. The only solution that has been was proposed and worked is that your source has ultra-relativistic speeds. It's moving highly relativistic. When this happens, the collision of the photons, because of the aberration of the light, the relativistic phenomena, it happens in very big angles, close to P. So the differential cross sector drops dramatically, and the photons can escape and reach to the observer. So this was the first, this was the strongest indication that you can estimate the Lorentz factor that you need for such a distribution, and you find them that you need the Lorentz factor of 100 to 1000, which are super relativistic. In AGNs, the Lorentz factor is about 10 of order of magnitude. Here we are talking for 1 or 2 orders of magnitude higher. Another thing that concerned the community at the 90s and early 2000s was the shape of the outflow. Okay, you have a relativistic outflow that expands, but what shape does it have? Is it aspherical, or is it a collimated like a jet, like the blazer that we are seeing? Theoretical arguments and mostly of energetic nature, were arguing in favor of a jet, of a collimated outflow. Rhodes at 1997 proposed an observation criteria for this called the bachromatic break. So imagine that you have a spherical surface that emits a sphere that emits from its surface that expands in the interstellar medium relativistically. As an observer that you are far away, you don't see the whole sphere. The aberration of the light forces you to see only a small part of it, which is equal 1 to gamma. I can show you a simple geometrical argument if you want. Yes. So we have the sphere that expands with a gamma factor. Due to the aberration of the light, if if we consider here a small part of the surface, it emits inside a cone of an opening 1 to gamma. Okay? So if you are an observer far away, what's the edge of the portion that you will see? It will be if we assume that it goes that in parallel. Okay, you will see only from that to here. Yeah, you will see only that part of the sphere. You will be able to see it. Okay? So imagine that you have, now that you have the sphere that goes outward, expands with a gamma, but at the same time, it also sweeps out interstellar material. As it expands, one process is that it cools down, so it becomes fainter. The other process is being that the visible arc circle becomes higher. So you have this factor that the one is against the other. But what you will have you should have in mind is that their combination results in a smooth decay of the observed of the received flux. Now, as the sphere expands in the interstellar medium and sweeps out material, it also decelerates. So its gamma is being reduced. If we have a jet, okay, we'll have these two contributions. We have the small surface and the cooling sphere. If we have a jet, and when we reach, when the jet Lorentz factor reaches to its extent, to the jet extent, then we stop to have the contribution from the more surface that was visible to us. So the received flux drops more dramatically, and you observe that break here, which is what we call the panchromatic break. If you measure this break, you will be able to understand also what's the opening of your jet. Despite our eagerness, when in 2004 the SWIFT launched, a new observatory launched in 2004, which is still operating. It's our main tool that we use in order to study GRBs. And after the analysis of the data it collected, it appeared that only a very small part of the GRBs had this panchromatic break, only 10%. Another part of them, they had chromatic breaks, and some others, they didn't have at all break. Nevertheless, the community believes strongly that there is a jet. So they proposed different explanations in order to describe why we don't see so many breaks as we wish. One of them is that the break appears later, and when the source is too faint in order for the telescope to have accurate observation, or that we are not, and this is a very nice explanation, very prominent, that in reality we are not laying on the jet axis, but a little bit sideways. So this thing has these results that the break is not so steep as you expect, but it becomes smoother, and so it's difficult for you to understand it. So the recent estimation for the jet opening for the GRBs are giving this value. They say that the value, the jet opening is about 10 or to 20 degrees. Later, before SWIFT, we were assuming that it was smaller. And if you assume that you don't have an isotropic emission and you have a jet collimated outflow, this means that the total release of the energy is not 10 to the 52 or 10 to the 54, but it drops to order of magnitudes below. Now we believe that the long gamma ray burst emits like 10 to the 51 ergs in their prompt phase. So after the main burst that happens, let's say, in the first 1,000 seconds, it comes the second phase that we call the afterglow, the remnant of the explosion. the received radiation goes from gamma rays to longer wavelengths, goes to X-rays, ultra visible, optical, infra, radio, and becomes fainter. This phase we call it the afterglow. For the afterglow, we know our knowledge is in a very good level. We do know what processes, radiation processors participate, and we know at what place of the burst of the phenomenon that radiation comes from. And more specifically, the afterglow comes with from the interaction of the jet of the jet head with the interstellar material. As the jet goes inside the interstellar medium, it creates an external shock, a shock on its edge, and at that point, through synchrotron processes, we get the afterglow spectrum. For the main phase of the burst, our knowledge is very low. There are many open questions, still open questions. First of all, we don't know exactly from what, we know that it comes from the body of the jet, the radiation, but we don't know exactly from what formation inside the body comes. Or we don't know even the radiation process that participates. In the 90s, there has been Banded and others had proposed that, had tried to fit the spectrum of the prompt emission with a double power law. This is called the band function. But later, when the Swift data came, which is more detailed and more extensive, we saw that this function doesn't fit all of the time. It fits only in very specific times, and you can get a better fit if you assume, except this one, except the power law, also modified, also a thermal radiation, a black body radiation. So today, that the band function might be ascribed to some non-thermal process, but we also need some thermal process. So today we apply that double fit. We use this double fit, and we try to understand what is happening inside the body of the outflow. Another thing I want to say is that we don't know about the magnetic content of our jet. Is it the pointing energy? Is it important? Does it the magnetic field? Does it play any significant role on for it? We don't know this, and this is because it's very difficult to have observation for the magnetic field in general. The only direct tool that we have is the Faraday rotation, when you can measure the change of the polarization of the light, and from this you can get an estimate for the magnetic field. There are some other methods that they are model-based. They are model-based. Model-dependent. They depend on what model you assume for your outflow. In GRBs, you cannot even have a polarization measurement, not Faraday result. You cannot even have one polarization measurement. After 2000, they have made some announcement that some researchers has used indirect criteria, like Coburn in 2002, to see what and try to discover what was the polarization of the GRB. Some of them they announced very high values, 70%. Some of them they announced for the same burst, 0. Some of them they re-examined the result of the first one. They said no, it was wrong. They made wrong in their own model. So with this thing, it's totally unclear to us. For the GRBs, we don't have any evidence from polarization. We cannot say there is a magnetic field or if there is not. Despite of this, the jet community believes in RMHD as a mechanism. So I'm coming from the RMHD community, so I do believe that there is a magnetic contact, but we still don't have a direct observational evidence for it. For their host, in '93, even with primitive data from the Compton Observatory, Cuvelier to make a very simple study, and she plotted the population, the number of the burst, as a function of their duration. TAF 90 is actually their duration. She found that, that their distribution, it has two peaks, one close to 1 second or to half second, and one close to 20 seconds. That result gave us a strong indication that actually the GRBs are in reality two totally different phenomena. There are the short GRBs with the duration from 1 millisecond to 2 seconds, and the long GRBs from duration from 2 seconds to 1,000 seconds. And those two we consider to be completely different phenomena. Of course, that distinction is not strict. You can have a short GRB with duration of 10 seconds. Today we have, because you can imagine there is a possibility here to exist such a short GRB. Today we have more advanced criteria, observational criteria, that we use in order to say if a GRB is short or gamma ray or long. What was important for us was the location of the host galaxies, the galaxies that the places that this burst occurs. For the long gamma ray burst, we found that most of the times the host in a galaxy is an early type with it is a dwarf galaxy or an early type, galaxies with intense star formation, star rate formation. While for the short GRBs, we found that most of the times are elliptic or spirals and out of their spheres, the places where this burst occurs, places where there is no significant star formation. That comes in association with the two types of progenitors that we have in mind in the 90s. In the 90s, there have been proposed two scenarios for the GRBs. The first one was referring to the collapse of a massive star, to the core collapse of a massive star. That has been proposed by Gousley, and they were calling the Collapsar model. The other idea was that the GRBs are coming from binary systems, binary systems of compact objects, from neutron star compact object, binary system, neutron star black hole system, etc. The identification of the host provide us now with the knowledge that we know now that the long GRB are coming from the collapse of massive stars, from the collapse of the core of massive stars, while the short one are associated with the binary system. The massive star has been specialized even further at the subsequent year, and they found to be, they assumed to be Wolf-Rayet stars, which are massive evolved stars with masses like the 20, 30, 50 solar masses. And at those stars, the core collapses, not the whole, initially not the whole star collapse, and it forms a black hole in its center. And around it forms a accreting region and a accreting disk. From that system, the accreting disk and the black hole, creates a jet that goes out and penetrates the stellar envelope. And then it goes out to the interstellar medium. The problem with these stars are that their evolution, their evolution is not well known, is not well established. First of all, there are many types of Wolf-Rayet stars. There are types N, type C, type SO from the carbon, oxygen, etc. For the gamma ray, for the long gamma ray burst, we believe now that the most appropriate type is the WO, the Wolf-Rayets. But the WO, Wolf-Rayets are in general short-living, and WO is even more rare than the rest type. So we don't have a good sample close to us to study it. And the whole approach is based mostly on theoretical models for the stellar evolution of the Wolf-Rayets. I think that it was of special importance for my research was if they have a wind and how thick and what is its density. The problem is that there are Wolf-Rayets that have a normal stellar wind of low density, and there are Wolf-Rayets that, like this one, they have a very dense cocoon, a very dense thick wind. So this is an open. This is something open that I will go to use later in my research when I will show you my research. And for their radius, okay, their radius, despite their mass, is not something monstrous. It's close to the solar one. There can be Wolf-Rayets with even smaller radius than the solar one, or to be very few solar radius in dimension. This is, I'm just showing it here. This is the paper that is the base for the most works made in long GRBs for the Wolf-Rayet structure. It shows the density in its radius. Here, you assume that is the surface of the Wolf-Rayet. This work contains many models, many different models of Wolf-Rayets. We make more than 30 cases. I will show you. Here is a very basic shape of what we have until now. Okay, we have the core, the black hole in the core of the star that has been collapsed, the accretion disk, and we have a jet that is being launched from that system and penetrates the star and continue outside to the interstellar medium. For simplicity, in the beginning, let's assume that the interstellar medium is of negligible density. The jet, as it goes out, it expands. And this is what we call, it suffers a rarefaction process. Rarefaction is a weak discontinuity. A weak discontinuity is a discontinuity not on the quantities of the outflow, density, pressure, the velocity. It's a discontinuity of their derivatives, of their first derivatives. It makes an acute angle if you plot them. As the jet goes out of the star, the information that inside the star there is a pressure that supports the jet. Outside of the star, the pressure is lost. The information that the pressure is lost is propagated in the flow of the jet. And using through this weak discontinuity, through the rarefaction front. Okay. Something to say here. When you are considering MHD model for the jet, you have the problem of the correlation of the Lorentz factor with the jet opening. The jet opening and its Lorentz factor are correlated and they're becoming equal to 1. So if we didn't have rarefaction, the question is that how the panchromatic break will occur. If we didn't have, we will always be close to that case where the opening of the jet is equal to the 1 over gamma jet. But there are some cases that the panchromatic break appears and the chromatic break appears. How can we accelerate jets and not fulfill that criteria? The answer is being given by rarefaction. In rarefaction, let's see here. If we accelerate the jet, it becomes more collimated. This is what says that relation. So with rarefaction, we don't have this problem. The outflow is being accelerated, as we will see. In rarefaction, we have a strong acceleration of the outflow, but it's not being further collimated. Actually, it becomes wider. So with this way, we find a natural manner to overcome the Kommissarov correlation criteria. Now, some things about the special relativistic 2D magnetodynamics. Okay, we know that the system of equation is highly non-linear and difficult to manipulate. The full form of the equation is the continued equation, the energy momentum equation, the equation of state that comes from microphysics, the Maxwell equations, and one equation that relates, that describes the reaction of electromagnetic field and matter, which is the Ohm's law. For environments like the ones that we are dealing, the ohmic resistivity is very low, and the outflow is considered ideally conductive, electrically conductive. If you want, you can assume axisymmetry. In the jets, we assume them most of the times. And there are the 7 waves of the theory, the 2 fast, 2 Alfvén, 2 slow magnetosonic, plus the entropy wave. And from the mathematical point of view, the problem is always hyperbolic, and that helps us to build very sophisticated algorithms, codes, like the Pluto, the Flash, that can integrate the outflow. In the steady state equations, in the steady state limit, the equations are the same, but you are having a vanishing time derivative. What is interesting is that in this set, the problem mathematically is more complicated. It's mixed type. Here is the fast surface, the fast magnetosonic surface. Here is the slow magnetosonic surface. Here is something else that we call the SCAP velocity, the Casper velocity. Here, the characteristic exists. 2 characteristics, let's say, exist. Here the same. Here null. Here the problem is hyperbolic. Here hyperbolic. Here is elliptic, elliptic. So you have a mixed type problem that is very difficult to handle it analytically. I want to show you some quantities because I'm going to use them later. Those are familiar for the steady state RMHD. One quantity that we use is this A. A is the flux of the polyidal field lines. When I'm saying polyidal, I mean the plane where the jet is propagating. Let's say the Z, H, or the cylindrical radius P. When I say toroidal, I mean the transverse, the plane of symmetry of the jet. Okay. So here is the flux of the polyidal magnetic field lines. If we assume that BP, the integration is performed on a surface that's on the toroidal plane, on the transverse plane. If the magnetic field, the polyidal magnetic field, goes in one direction all over across the jet, this is a monotonous function, and you can use it in order to label from its value every polyidal field line. This is the Alfvénic Mach number, an Alfvénic type Mach number. This is something that is trivial in the RMHD. This is the magnetization parameter. It shows it is the ratio of the pointing of the magnetic energy of the pointing flux of the magnetic energy to the total energy of the mass, to the flux of the total energy of the mass. Also, in the steady state RMHD, we have found that there exist 5 field line integral quantities that they remain constant along a specific field line. Okay. What we are going to use here, okay, this is the ratio of the flux of the mass of the magnetic. This comes from Ferraro's law. This is the specific angular momentum. This one is more important for us. Is the total energy, the total flux of the energy, normalized to the mass flux, and is the total energy. Let's have it like this. And it has two parts. One is gamma h, which is the thermal part, the thermal energy, and the other is the gamma h sigma, which is the magnetic energy. Okay, the total energy is the sum of these two contents. And this comes, and finally, this comes from, is the adiabatic invariant, comes from the polytropic equation of state. If you assume that these integrals, you need two equations to integrate. You left by two equations to integrate. The first one, we call it, it is the Transfield equation, and it's actually the projection of the energy momentum equation to on the poloidal plane and perpendicular to the field lines. In this equation, R is the curvature radius of the field lines. He is the cylindrical distance, the cylindrical coordinate, normalized to the light cylinder radius. And the second equation is the Bernoulli equation. Is an equation that we use in order to substitute one of the complicated that the energy momentum equation provides us, and we substitute one of their component with this one, which is linearly dependent with the other ones, with the rest. And in the 90s and the early of 2000, they have made there has been a lot of effort in order to find a semi-analytical description of the steady-state jets. It was a difficult problem, and the problem is it was that it is very difficult to find a solution that passes through the whole critical surface, through the slow magnetosonic, through the Alven, through the fast one. The first that succeeded this was Professor Vlachakis and Professor Koenigl in 2003, which they used the self-similarity, the R self-similarity property, to find a solution in the jet outflow. What is R self-similarity? Okay, because just a minute, we have a technical problem. It's not that it's started. Switch off and on the presentation. F5. No, it's just the laptop. The whole? That's the question. Is the problem with the presentation or with the laptop? With the.